Welcome to This Explainer. Today, we're going to take a methodical, objective, and highly technical look at a really fascinating piece of research. It's a 2026 paper by Gain and colleagues. We're going to be deliberately pacing our discussion today, taking our time and slowing down just a bit to really unpack the mechanics of this structural breakthrough in multiscale modeling. So, if you're focused on understanding how engineering and artificial intelligence are merging at a fundamental, thermodynamic level, well, you're in exactly the right place.
To establish our groundwork, we're drawing directly from their paper, which was published in the journal Computer Methods in Applied Mechanics and Engineering. The core challenge here is computational. Basically, how do we accurately, yet efficiently, model the intricate mechanical behavior of woven composite materials? Woven composites are incredibly useful because they can form so easily to complex curvatures. But, computationally, their interlaced structure is notoriously difficult to simulate.
Okay, let's dive into this. Here is our structural blueprint for today. We'll cover the computational homogenization challenge, the limitations of standard AI, encoding physics into PRNNs, building the hierarchical architecture, validating the results, and finally, wrap up with the future of materials analysis. Part 1. The computational homogenization challenge. Let's look at why bridging information across multiple structural scales causes such a massive computational headache.
Visually, this is the challenge. We're zooming in from a macroscopic composite sample at the top, down to the mesoscale where fiber yarns interlace, and then finally down to the microscale, which reveals the highly detailed finite element mesh of the individual elastic fibers embedded in an elasto-plastic matrix. The morphology is incredibly intricate, and the nonlinear behavior of the material originates all the way down at this microscopic level.
So the crucial point is this. Standard computational homogenization requires us to solve microscale interactions at every single mesoscale integration point for every single time step. Because we're linking microscale information all the way up to the macroscale, this actually requires two distinct scale transitions. In the engineering world, this is known as an FE3 approach. And practically speaking, it creates a totally unmanageable computational bottleneck. It's just simply too expensive and way too slow. Part 2. Limitations of standard AI. To bypass this intense computational cost, engineers have naturally turned to data-driven machine learning as a potential alternative. Let's objectively contrast the two approaches here. Standard data-driven AI models, like your conventional recurrent neural networks or transformers, suffer from heavy data dependence and limited interpretability. It's the classic black box problem. But more importantly, and this is a fatal flaw for engineers, they're highly prone to nonphysical errors when asked to extrapolate beyond their training data, especially when we're dealing with path-dependent behaviors like plasticity. Physics-encoded AI, on the other hand, mathematically embeds real-world thermodynamic constraints directly into the network. This makes them highly interpretable, robust when extrapolating, and honestly, just much more data efficient. Part 3. Encoding physics into PRNNs. And this brings us to the foundational building block chosen by the researchers to solve our FE3 bottleneck, the physically recurrent neural network, or PRNN. The researchers map their neural network architecture directly to computational homogenization principles. It happens in 3 neat steps. First, localization. An encoder network acts as a downscaler, mapping mesoscopic strain inputs to local points. Second is the material layer. Here, a classical constitutive model basically replaces standard neurons to update internal variables. Third, homogenization. A decoder network acts as an upscaler, aggregating those local stresses back into a mesoscopic stress prediction. It perfectly bridges the machine learning lexicon with finite element concepts. And this brilliantly illustrates the inner mechanics of that material layer, specifically those gray boxes right in the center. Instead of standard scalar activation functions, neurons are grouped into sets known as fictitious material points. Each point explicitly calculates stress and updates internal variables, like plastic strain, using an embedded elasto-plastic constitutive model. This means path dependency emerges naturally through physics rather than relying on the opaque, hidden memory states of a standard recurrent neural network. Part 4. Building the hierarchical PRNN. Now, while the PRNN works great for a single-scale transition, woven composites actually require a 3-scale response. Let's see how they build this up to the mesoscale. To address the incredibly complex architecture of woven composites, the researchers developed the hierarchical PRNN, or HPRNN. They take the micro-PRNNs we just discussed, pre-train them to learn the fiber matrix interactions, and then freeze their weights.
These frozen micro-PRNNs are then nested into a larger meso-to-macroscale network. The new material layer integrates three distinct modules: a pure J2 plasticity matrix model, a module for the warp yarns, and a module for the weft yarns.
Now, modeling those weft yarns requires a highly efficient trick. Woven composites have a strongly orthogonal nature, right? So instead of running entirely new high-fidelity simulations to train the weft network, the researchers use a standard 90-degree tensor rotation around the z-axis. It's essentially a brilliant computational shortcut. This allows the weft yarn stress and strain behavior to be derived straight from the existing warp dataset. It's a highly efficient way to capture the material's orthotropic behavior without doubling the computational cost of data generation.
Part 5. Model Validation and Results. So, we've built a hierarchical network that embeds classical physics straight into its latent space. The critical question now is, does this actually pay off when we look at the data?
Now, what's really interesting about this slide, looking at figures 11, 14, and 19, is how the network's complexity correlates with accuracy. By tracking validation errors across distinct loading paths, we see stability emerges with just a few fictitious material points. This proves the HPRNN can capture complex microscale responses without bloating the network. It demonstrates that you really only need a relatively small, highly focused material layer to accurately map these incredibly complicated transitions. But the true test, that is extrapolation. Take a look at figure 18 here, mapping in-plane stress-strain behavior under complex cyclic shear loading. Standard gated recurrent units, or GRUs, they fail completely here, predicting nonphysical overlapping loops. The HPRNN, however, extrapolates beautifully to this unseen cyclic data, strictly obeying thermodynamic constraints and doing it in just a fraction of the time a traditional finite element simulation would take.
Part 6. The Future of Materials Analysis. Let's step back for a moment. We've gone deep into the methodology today, but what does this structural breakthrough actually mean for the broader computational mechanics community moving forward?
The fundamental takeaway here is all about bridging the gap. For years, engineers have had to choose between the physical rigor of computational homogenization, which is way too slow, and the efficiency of machine learning, which historically couldn't be fully trusted with complex, path-dependent physics. The hierarchical PRNN provides a pathway that is both computationally efficient and inherently interpretable. It gives engineers a multiscale modeling tool that they can actually trust under diverse loading conditions. I should point out, this structural breakthrough was developed by the Mechanics and Physics of Materials Research Group over at materialslab.org. Their contribution to integrating neural network surrogates with strict physical laws really marks a vital step forward in composite modeling. Which leaves us with a final provocative thought. We are seeing artificial intelligence frameworks that no longer just guess the physics, but actually compute them through embedded thermodynamic constraints. As these surrogate models achieve true physical recurrence and massive computational speedups, we really have to ask, will traditional, nested, multiscale, finite element analysis eventually become a thing of the past? It's a fascinating question for the future of engineering. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you next time.